This is section 3.8, derivatives of logarithmic functions. Our first objective is to compute derivatives of exponential and logarithmic functions. By the time you're done, I'd like you to be able to explain the similarities and differences between the two exponential derivative rules and the two logarithmic derivative rules. That means we're getting after 4 different rules in this objective. So in order to do that, we're first going to connect to our old knowledge. We're going to combine what we know about the derivative of e to the x, the old properties of exponents and logs that we learned last year and in Algebra 2. We're going to remember what we know about inverses, and we're going to use implicit differentiation. So we're going to put that all together to develop rules for any exponential and any log function. So to get started, let's recall that if I take the derivative of e to the x, I just get e to the x. It's exactly the same thing. Let's also recall from pre-calculus that if y equals e to the x, that's the exact same thing as saying x equals the log natural of y. It's kind of like if I have a 3 plus a 4 equals a 7, I can do the inverse operation of addition and get 4 equals 7 minus 3. So this exponential and a log of base e are inverses of each other. So this has the exact same information in it as this expression here. So now let's apply both of these to our rule for derivatives of logs. If we want to get the derivative of the ln of x, we're going to let y equal the ln of x, and then we're going to rewrite it using this rule that we had up here. So instead of writing y equals ln of x, we can rewrite it as e to the y equals e to the ln of x, which is the same as just an x. So I've got e to the y equals x. Now what's nice about this is that I have a rule for taking the derivatives of e's. So if I differentiate both sides with respect to x of this equation, I will get the derivative of e to the y equals the derivative of x. Here on the left, I hit the e first and leave it alone, and then I hit the power, whose derivative is just dy dx. On the other side, the derivative of x is a 1. If I then isolate dy dx, like I did with implicit differentiation in section 3.6, I would have dy dx equals 1 over that e to the y. But going back up to the beginning, we can see that e to the y is the same as x, and because it is, we can substitute out this e to the y and have an x instead. That helps us develop this natural log rule, which is the derivative of log natural of x is just 1 over the inside. So whatever's inside here is going to get dumped into the denominator. So let's look at some examples that utilize that log rule. If I want to take the derivative of this, I'm going to have to apply the chain rule in addition to that log rule. So when I hit the log, the rule for taking the derivatives of natural logs is just 1 over the inside. Now because that inside was something other than just a plain x, I have to use the chain rule and multiply by the derivative of that inside. If I do that, I end up with 1 over x. Now here's what's really interesting. If you remember your old log rules, we know the log natural of 2x is the same thing as the log natural of 2 plus the log natural of x, because interior multiplication is the same as exterior addition. So if I take the derivative now, I'll get dy dx equals the derivative of the constant, which is 0, plus the derivative of ln of x. Notice I get the exact same thing, whether I use the chain rule or I use properties of logs to break it apart. If we look at this next one, again, we can use the chain rule with the log rule and have 1 over the inside unchanged times the derivative of the inside, which if I finish will give me a 1/2 over a root x times a root x is just an x. Again, we can use our log rules and remember that interior powers are the same as exterior coefficients. And then when I take the derivative, I'll move through the constant and hit the log. And notice I get the exact same thing, whether I use my log rules and then take the derivative, or I just take the derivative using the chain rule. Last one, we want to use the product rule because I have two things multiplied together. So I will have dy dx equals the first one times the derivative of the second, which I hit that log first and then I hit the inside, plus the second one times the derivative of the first. I can simplify if I care to. I can see that I've got a 12x squared on top and a 3x squared on the bottom, so that gives me a 4 plus a 2 ln of 3x squared. With example 2, we have a line with slope m that passes through the origin and is tangent to the graph of ln of x. So I can draw my ln of x, which crosses through the point 1, 0 and has an asymptote here. Notice that it doesn't pass through the origin at all. So we're looking for another point on the curve that will be tangent, or that will create a tangent line that passes through the origin. So here's that favorite part of mine, favorite problem type that we keep doing over and over. So I have the point a ln of a. There's my general point. And I have the general slope, which will be the derivative of this with an a plugged in, which is 1 over a. Once I have the point and I have the slope, I can write the equation of the line, which is y equals the slope times x minus the x coordinate plus the y coordinate. Notice now that I can plug in the point 0, 0, and it must make the sentence true. When I do that, I get 1 over a times a negative a is just a negative 1. And I can move that negative 1 to the other side, and then I can get rid of the logs by raising both sides to the e. So I end up figuring out that a equals e. Because a equals e, the question is, what's the value of m, which is the slope? So I'm going to come back to here and figure out that my slope is 1 over m, 1 over a, which is 1 over e. Next, we want to develop a general rule for the derivative of a to the x. So to get there, again, we're going to let y equal a to the x, and then we're going to rewrite it so that we can use rules that we already know. We don't know how to do an a to the x, but we do know how to do log natural of x's. So I can rewrite this by logging both sides and then moving this x to the front. Notice now that I have the log natural of y equals x times the log natural of a, and I can differentiate both sides with respect to x. So the derivative of the left side would be 1 over the inside, which is y, times the derivative of the inside, which is dy dx. Now this side gets a little tricky because people forget that this ln of a is just a constant. So if I have x times a constant, then the derivative is just the constant. So here's that constant here. I can multiply both sides by y in order to isolate dy dx, and then I can replace y with what it originally equaled, which was a to the x. So now I have a general exponential rule that looks an awful lot like the e to the x rule. What's different is we repeat like we did before, only now we're going to multiply at the back by the log natural of that base. If we use that particular rule now with example 3, we can see that the derivative with respect to x of 3 to the 2x, I have an exponential, so it will stay the same. And then, because the base was not an e, I have to multiply by the log natural of that base. So here's the exponential rule applied, and then I have to multiply at the back by the derivative of the power. Same thing here. The first thing that I hit is the exponent, or the exponential expression. So I will leave it alone, and then multiply by the log natural of the base, and then multiply by the derivative of the power. Last one, notice I have a product involved, so I will have the first one times the derivative of the second. Well, the derivative of the second, I hit the exponential first, so I leave it alone. Since the base is not an e, I multiply by an ln of 4. And then, since my power is not just a plain x, I apply the chain rule to get the 3. So here's the first times the derivative of the second, plus the second times the derivative of the first. With example 4, it says, at what point on the graph of this function does the tangent line have a slope that is 8 log natural of 2? So that's asking when the derivative of this, which is 2 to the x times the log natural of the base times the derivative of the x, which is 1, minus 0, has to equal 8 ln of 2. Well, that's a 2 to the x times the ln of 2. I want that to equal 8 times the ln of 2. I can divide off the ln of 2 because it's not 0. And then I can figure out that x is going to be 3 because 2 cubed gives me 8. The goal was to find the point, so I have the x-coordinate. To get the y-coordinate, I'll plug the 3 in. That'll give me an 8 minus the 3 is a 5. The last rule we want to develop now is the derivative of a general logarithm. So notice that I have a base other than e on this. So to get there, again, we'll let y equal the log base a of x, and then we'll rewrite using properties of exponentials. So remember from last year that you can start with the base and go around the circle. So we'd have a to the y equals x. That's equivalent to this for the same reason that adding is equivalent to subtracting. You can write the same information in an equivalent statement. So here I have this a to the y equals x. I differentiate both sides. So the derivative of a to the y will be a to the y unchanged times the log natural of the base times the derivative of that power, which will be a dy dx. And on the right-hand side, we will take the derivative of x with respect to x and get a 1. If I isolate dy dx, notice that this all ends up on the bottom. But what is this a to the y? The a to the y was the same as x. So we can see that this looks an awful lot like the derivative of a natural log because it's 1 over the inside. What's new is that I have that ln of a on the bottom. So just like when I did the derivative of e to the x, and I got the same thing, and when I did the derivative of ln of x, I got 1 over the inside. Well, if I change the base, I'll get the same thing times that ln of a. And if I change the base here, I'll still get 1 over the inside, except now I have that ln of a. Now I want to show you something because these two are actually just special cases of these. If I multiply by the log natural of the base, that's just a 1, so I get that e to the x. Same thing down here, if I multiply by the log natural of the base, it's just a 1, so I get the 1 over x. So in reality, we just have 2 rules to memorize as opposed to 4. With example 5 now, we want to apply that logarithm rule for general logs. On our first one, dy dx will be 1 over the inside times the log natural of the base times the derivative of the inside. Notice the 2's will cancel, and I get 1 over x times the ln of 5. With this one, my dy dx, the first thing I hit is the log. So the log does 1 over whatever's inside of it times the log natural of the base. And then I must multiply by the derivative of the inside. Since that is a third power, I'm going to apply the power rule. And then multiply by the derivative of the most inner inside, which is a 1. And I'll just let you leave it like that. Lastly, we'll take the derivative. The first thing we hit is the log, so it's 1 over the inside. Times the log natural of that base. And then because the inside was more complicated than just a plain x, I have to take the derivative of the inside. So the derivative of the inside, I'll hit a cosine, which would be a negative sign, of its inside unchanged, times the derivative of its inside, which is 3, plus, now I hit the sine, derivative of sine is the cosine of the inside unchanged, times the derivative of the inside. And we're done. So for the rest of this, you have some notes web exam problems to do, and then I'd like you to explain the similarities and differences between those 4 derivative rules for logs and exponentials.